Hello, everyone. Let's take a look at this Newton's laws problem. This is a dynamics problem because there's going to be acceleration. So we have these two blocks. They're connected by a pulley. So one of the blocks, the M1, has a mass of 4 kilograms. Block 2 has a mass of 8 kilograms. So when you see something like this, you can imagine having a physical model of this and try to think about what would happen to the two blocks once you let go. And because M2 is more massive than M1, you can predict what would happen, which is that M2 will drag everything down, right? And M1 will get pulled up a bit. So it's always good in a case of a dynamics problem to think about, okay, if you let go, set things in motion, what would happen? In this problem, there is friction between block 1 and the ramp, so we have to factor that in. The objective here is to find the acceleration of the system. We are going to ignore the effect of the pulley, so we don't want to think of the pulley as a disk that has a moment of inertia, things like that. We're going to simplify things and assume that all that the pulley does is change the direction of the rope, the cord or the rope that's connecting these two blocks. All the pulley does is to just kind of change the direction and just kind of rotate without any friction. It just doesn't get in the way. So that's an assumption. It's a simplifying assumption, but we'll keep it simple for now. And so we're going to assume that we're going to essentially ignore the pulley. Okay, so you know that this is a Newton's laws problem. What does that mean? You have to apply F equals ma, so we can start jotting that down. So we know that the sum of all the forces should equal mass times acceleration. And you know by now that even though we write this in this compact form, what we really mean is to sum forces in the x direction, set that equal to mass times acceleration in the x direction, and then we do the same thing for the y direction. Always good to start with the big idea. The big idea is to apply Newton's second law in the case of constant mass, F equals ma, to this situation. We should also think about drawing free body diagrams. There are two blocks, so what we're going to do is draw two free body diagrams. Let's start with block 1. Right, so in its orientation, I just keep things in the same orientation as the problem gives. And block 2, draw block 2 like this. And what we want to do with the free body diagram is to put all the external forces that's acting on each of these objects. So let's start with block 2. We have the tension going up and its weight pulling down, so that's its weight. And when we have a free body diagram, we should also think about what's our coordinate system like. In the case of block 2, it's okay to just stick with your standard xy coordinate system. So here's your x and y. No problem sticking to the regular xy coordinate system there. In the case of block 1, what are the external forces acting on block 1? Well, there's the normal force off the ramp onto the block, normal like 90 degrees, right? So we have a block M1 and its normal force points like that coming up. What else is here? There's this rope connected to M1 and the tension here is going like so. A point of confusion is the fact that the tension force changes direction depending on which object you're considering. And remember, for a free body diagram, it's the perspective that matters. If you're talking about block 1, from the perspective of block 1, what is the rope doing? The rope's trying to pull it up. From the perspective of block 2, what's the rope doing? The rope is trying to pull up on block 2. It changes direction because you're considering it from each of their perspectives, right? So in terms of block 1, points upward to the right like this. What else is there? Well, its own weight is there, right? Remember, weight is always towards the center of the Earth, so don't get confused by the fact that this block is actually at an incline, at an angle, but still its weight points directly down towards the center of the Earth, right? And we have one more force here, right? We have friction. Block 1 is being dragged upward to the right, so the kinetic friction that is acting on block 1 is pointing this way, right? It's opposing that motion. Okay, so we have the free body diagram for block 1. Again, just like with block 2, let's think about a coordinate system. And in this case, it is to your advantage to rotate the coordinate system. The two different free body diagrams can have two different coordinate systems. You don't have to use the same one for both. You can if you want to, but in this case, it is to your advantage to think of x going like that and y going like that, right? So I'll call this x prime and y prime so that we keep those separate, that there are two different coordinate systems. You don't have to call it x prime and y prime. You can just call it x and y, but just to keep it different, it's just good to put the primes. Okay, so why did I say that this is to your advantage to rotate the coordinate system? Notice that by rotating the coordinate system, the tension force is all in the x prime direction. The normal force is all along the y prime direction. The force of friction is the negative x prime direction. So that means you don't have to break up the vector into component parts because they're all in one direction or another. The only one you do have to break up is the weight, right? Because the weight vector, according to this coordinate system, points a little bit in the x prime direction and a little bit in the y prime direction. So we have to break up the weight, okay, make a right triangle. Remember, you make a right triangle by following the y-axis and the x-axis, right? So use the vector itself as the hypotenuse of the right triangle, and then you can find the other two sides. Notice that you only have to break up one vector when you're doing f equals ma, so you want to think ahead. We know we have to do this, right? X and y, we have to do it f equals ma in the x direction and the y direction. We're thinking about components, we're thinking ahead and thinking, how do I make my life easier? Much easier to break up one vector as opposed to four, right? So when you're thinking about coordinate systems, that is the conversation you should be having with yourself is this going to make my life easier? If you're dealing with a statics problem where the sum of the forces is equal to zero, right, there's no acceleration, then that is only the consideration you should be thinking about. You should be thinking about how do I minimize the number of times I'm breaking up the force vector into components. In dynamics problems like this, right, when it involves an acceleration, there's another consideration, and that consideration is the acceleration. Is better a lot of times if you can make sure that the acceleration's along one axis, not two. If it's along two axes, you can break it. It's a vector after all, and you can break up the acceleration into component parts. But in this case, block one, right, we know it accelerates along the ramp, right, upward to the right. And in our coordinate system, that's the x prime direction, right? The acceleration's all along the x prime direction, and we don't have to break up the acceleration vector itself. So in dynamics problems, there's another consideration, that's the acceleration. Now that we have the free body diagram for block one, the only thing that's missing is breaking up the vector weight, right, into component parts, and to do that, we need this angle. I can argue that this angle is 37 degrees because this angle is 37 degrees. There's a quick way to identify this, right? It's not obvious by looking at this diagram that 37 degrees as shown on the diagram is the same angle in the free body diagram. So I'm going to make a separate video of how to quickly identify those two angles are the same. But for now, show you that this angle is the same and kind of move on, but I'll later explain why and how you can quickly identify that angle is the same for yourself. Okay, we have the free body diagrams for each object. Let's now apply F equals ma. So on the left-hand side, I'm going to put all the equations for block 1. On the right-hand side, I'm going to put all the equations for block 2. Let's start with block 2. It's a little easier to deal with the forces. Only two forces are acting on it. If we sum forces, you can look at the free body diagram for block 2 and realize, well, there's nothing going on in the x direction, so you can skip doing F equals ma in the x direction. You can write it down, but it's not going to tell you much, right? There's no force there. We can skip that and go ahead to summing forces in the y direction. So let's do that. Tension is positive, so you have tension as a positive quantity. The weight is negative, right? So the negative y direction, and we have that equal to an acceleration, right? So block 2 is accelerating, so you shouldn't set that equal to 0. So we'll say mass 2, that has to be specific, right? So when you say mass times acceleration, which mass, right? And then we'll be very specific about the acceleration, ay, right? Because there's an acceleration in the y direction according to its own coordinate system, right? In the vertical direction, it's going to go downward, right? So there is a F equals ma. You sum the forces and you set it equal to mass times acceleration. You want to put a negative here, and that is to keep things consistent. If you don't put that negative, it's not going to be quite right. Okay, because why? When you know the acceleration, you know which way it's going to go, you want to go ahead and put the signs in. Notice that our coordinate systems are independent, right? So the coordinate system on block 1 is its own, block 2 is its own. We want them to be consistent, right? Because we know that block 1 traveling in the positive x prime direction is going to cause block 2 to go in the negative y direction. So the acceleration in the case of block 2 is a negative quantity. So because of that, you want to throw a negative in there. This is not the only way to do it. This is kind of what I would do. I would set up the coordinate systems. I would think about the acceleration. And if I know, oh, I expect it to be going down, then I'll put a negative. If I expect it to be going up, I'll just leave it positive. Another way to do this is when you, let's say, set up the coordinate system like this for block 1, knowing that it's going up and to the right, in the positive x prime direction, you could set up block 2's coordinate system such that its y is positive downward, and that would be consistent, and then you wouldn't have to do this negative thing because it would be accounted for. If you did it that way, it gives you the same result. So if you prefer that, fine, you can do that. But I just prefer doing it this way because, I don't know, it makes more sense to me this way. Okay, so what I can do here is solve for the tension. Tension's equal to minus m2 ay plus m2 times g, right? Because I can substitute what the definition of weight is. Weight is mass times the acceleration due to gravity. So I can go ahead and rewrite the weight as m times g. We'll pause here on block 2. Again, our objective is to find acceleration, right? So we're making progress. We're getting some equations going, right? Block 2 is a little bit easier to work with, so that's why we're starting there. Now let's switch over to block 1. Again, summing forces, right? We want to sum the forces. In this case, you want to do both directions. So we'll start with summing forces in the x prime direction. So looking at our free body diagram, you see that the tension is positive, right? Positive x prime direction. Friction is in the negative x prime direction. The normal force is not in the x prime direction, so we leave that. The weight, right? Notice that some of the weight, particularly this part of the weight, is in the x prime direction. So you want to use SOHCAHTOA to figure out what that is, and notice that's a negative direction. So you have a negative weight sine of 37 degrees. So those are the forces in the x prime direction. Running out of room, so I'm going to write it here, is equal to ma, right? So mass 1, acceleration in the x prime direction, right? So F equals ma. Now we come to summing forces in the y prime direction, okay? So going back here, the normal force is there, right? So positive normal force minus, there's a part of the weight, right? So notice that this part of the weight is in the negative y prime direction. So we need to include that. We'll say the weight cosine of 37 degrees. And what do we set this equal to? Is it sum of the forces equal to ma? Well, that's where we want to come here and realize, okay, look, the block 1 is only moving along the ramp. It's not levitating. It's not burying itself into the ramp. So it doesn't accelerate in the y prime direction. It's only accelerating the x prime direction. We can bring that in. So we're allowed to bring in that knowledge, right? We know it goes along the ramp, so then it doesn't accelerate in the y prime direction. So we set that equal to 0. This allows us to solve for the normal force using the second equation, the y prime equation. The normal force is equal to weight cosine of 37 degrees. Again, we can rewrite weight, right? m1 times g cosine of 37 degrees. Right, so that's the second equation. Kind of rewriting the second equation, we can get the normal force. Now the first equation, we can use that too, right? So what I'm going to do is just rewrite it. So the tension minus the force of friction, which is the coefficient of kinetic friction times the normal force, minus the weight, we can rewrite as m1 times g sine of 37 degrees. is equal to m1 acceleration in the x prime direction. Let's solve for tension. Kind of looking ahead here, why am I solving for tension? Well, because on the block 2 equation we solve for tension, the question didn't ask about tension. We don't care about the tension, right, for the sake of solving the problem. So we can solve for tension on both sides, right, for block 1 and block 2, set those equations equal to each other, and that will help us figure out what the acceleration is. Okay, so let's try to isolate tension for block 1. Tension's equal to, moving all the terms to the right-hand side, so we have on the right-hand side m1 acceleration the x prime direction plus mu k times the normal force plus m1 g sine of 37 degrees. Okay, so solving for tension on the left side of our work for block 1, tension's equal to this expression. So what we can do is, since we know what the normal force is up here, we can substitute. So we'll write tension is equal to m1 acceleration in the x prime direction plus mu k m1 g cosine of 37 degrees plus, I'll write it down here, m1g sine of 37 degrees. So now we have an expression, well, two expressions for tension. We have the expression here from block 2, and we have this expression here for block 1. So what we're going to do is set those equal to each other. We're going to set tension on both sides equal to each other. And this is what it's going to look like. m1 acceleration in the x prime direction plus mu k m1 g cosine of 37 degrees plus m1 g sine of 37 degrees is equal to minus m2 ay, acceleration in the y direction, plus m2 times g. One thing we can do to simplify that expression is to come back here and think about our acceleration. We've been careful to call the acceleration of block 1 ax prime, of block 2 ay. Been careful to call the two accelerations different things. However, something to realize is that if block 1 accelerates by some amount, then block 2 should have the same magnitude of that acceleration. If they don't, then what you're saying is that the rope is either stretching or compressing. So assuming that this rope is always in tension, that it's not stretching out, it's not breaking, it's staying rigid and staying as one unit, then making that assumption, the two accelerations of block 1 and block 2 should be the same. Imagine if the acceleration of block 2 was 3 times as high as block 1, well, what would happen is that the rope would break, right? Because block 2 would accelerate away and block 1 wouldn't be able to keep up, so then the rope would break, potentially. So assuming that it doesn't happen, what we can say is that the acceleration in the x prime direction of block 1 has to equal the acceleration of block 2 along the y direction. Right? These are magnitudes, so we're not really looking at the direction here. The magnitude should be the same, and if that's the case, we can just call all of these just a. So that simplifies our equation, m1 times a now, plus mu k m1 g cosine of 37 degrees plus m1 g sine of 37 degrees is equal to minus m2 a plus m2 g. Our objective is to solve for a, so we're going to try to put all those onto one side of the equation. So we'll say m1 a plus m2a is equal to m2g minus mu k m1 times g cosine of 37 degrees minus m1g sine of 37 degrees. We're going to factor a on the left-hand side. When you factor, it'll have a times m1 plus m2. So then on both sides, if you divide by m1 plus m2, you will isolate a. So on the left-hand side, you will have a is equal to m2 times g minus mu k m1 g cosine of 37 degrees minus m1 g sine of 37 degrees divided by m1 plus m2. One of the things that we're doing is avoiding the urge to plug in numbers, right? Notice that M1 and M2, we knew what these masses were the whole time, but it's not a good idea to start plugging those numbers in way at the beginning. Look at how much algebra we have to do, and imagine you just have to keep writing 4 kilograms and 8 kilograms over and over and over again. So you want to try to avoid that. Try to keep things in variable form. It makes it very clear. You can see what you're doing. Somebody else can see what you're doing. So you want to be very clear. Once you're at a place where you have what you need, you have the acceleration equal to some expression, now you can go ahead and put the numbers in. So you can say A is equal to 8 kilograms times 9.8 meters per second squared minus mu k, the coefficient of friction, 0.4, 4 kilograms, then 9.8 meters per second squared, cosine of 37 degrees minus 4 kilograms, again 9.8 meters per second squared. I'm running out of space, so what you should multiply here is sine of 37 degrees, okay? And divide the whole thing by m1 plus m2, which is 4 kilograms plus 8 kilograms. Okay, so if you put that in, you'll get that A is equal to 3.5 meters per second squared. Okay, so there's the problem. We found the acceleration of the system is going back to the philosophy of solving these sorts of problems, right? So dynamics problems involves acceleration. It's Newton's laws problems involving acceleration. Follow what you've done before for static problems. So you know you sum forces, that part you've done before. The accelerations may be something new to consider, right? How to think about the direction of acceleration, things like that. Are they connected, right? If they're connected as a rigid object, then the two blocks would have the same acceleration in terms of the magnitude. These are some things to consider. So we do simplify problems, right? So when you're looking at a situation like this where the pulley is involved, you might think, okay, in the real world, the pulley is going to affect this somehow. Yes, it does, right? And there's a way to deal with the pulley. Later on, we can talk about that. But when you're doing this sort of problem, just purely involving Newton's second law for linear motion, right? F equals ma, we'll ignore the pulley, essentially using the pulley just to change the direction of the rope. Make sure you're drawing your free body diagrams. Put all the external forces onto an object, right? So if we're considering block one, what external to block one is affecting block one forces, put all the forces there. Think about the coordinate system, right? And use one that is to your advantage, right? Minimize the work you have to do. And once you do F equals ma, you sum up forces in the x direction and the y direction, then it becomes algebra, right? So this looks maybe like a lot of work, but believe it or not, the algebra is easier to do as long as you follow the steps and make sure you're doing things that are valid algebraically, right? As long as you do things to both sides of the equation, then as long as you follow the algebra, you can get to the answer, right? But when solving Newton's laws problems, I would encourage you to spend a lot of time at the beginning of the problem, drawing free body diagrams, thinking about what F equals ma is, what are the forces going in, what's the direction, positive, negative, is there an acceleration, isn't there acceleration? So don't rush through this step, doing the free body diagrams part and doing F equals ma, because if something's wrong up there, then once you get into algebra, it makes it worse. Wait for the algebra, take your time, work through this part of this, spend a lot of time here, and then you will be able to solve not just this problem, but anything that looks like this, right? So in physics, you'll see problems that are slightly different, where the blocks are maybe not at an incline like this. Maybe one of the blocks is hanging off of a table, where block one is now on a flat surface, things like that. They may look different, but they're all following the same sort of recipe, right? This sort of recipe that we're doing. So as long as you get comfortable with this setup, right, setting things up this way, very systematically, very methodically, then you should be able to solve many of the dynamics problems that you're going to encounter.